In the last class, we had discussed different types of memory and how they can be interfaced with microcontrollers like ARM. In today's class, we shall look at the memory organization, how these different types of memories are used to set up the complete memory system in an embedded system. So, let us have a look at what we call a memory centric view of the embedded system. We have the CPU here, and this is a cache memory, a fast memory, which is typically would be SRAM, static RAM, and this is a level 1 cache, that is why we call it a L1 cache. There is another area of memory which is also on chip, and this is called scratch pad memory or SPM. This is also would be typically RAM and not DRAM. Off chip memory is the memory which is outside that of the chip boundary. So, these are the very basic components. Now, what we shall look at is what are these components, how they can really be organized and used. So, memory system in an embedded appliance starts with the register file, which is typical to that of the microcontroller which is being used in the embedded system. There may be one or more cache memory that feed data and instructions to the pipeline, because most of our microcontrollers that we have studied are pipelined processors. Main memory system may be contained partially on chip and partially off chip. In fact, scratch pad memories have been proposed as one form of what we call high speed on chip memory. Off chip memory can include a variety of technologies, that is memory made with a variety of technologies including synchronized DRAM, because synchronized DRAM gives you fast data access, particularly in burst mode synchronized with the system or bus clock. So, if we look at the memory map of the processor, this is a complete memory map, and the scratch pad memory is basically on chip memory, and we have seen that different processors have different amounts of on chip RAM. So, these we can think in terms of a scratch pad memory. This memory DRAM is typically off chip memory, which occupies a portion of the address space, memory address space of the processor, but it is typically resident outside that of the chip. This is what we have shown as a data cache. Now, it may have instruction as well as data. So, I have got an unified cache. There may be separate data and instruction cache. So, that will be the case with Harvard architecture. So, here we are simply showing a data cache, and what is interesting that you will find that this data cache is mapped onto the address space of the DRAM, and that is typically the feature of cache memory. So, in terms of access speed, your scratch pad memory should be typically synchronized with a one cycle, that is same cycle clock cycle as that of the CPU, so that accessing this memory does not need wait states. Okay. In case of DRAM, if we have shown here typically 10 to 20 cycles, so it might require wait state, and that is why that memory is expected to be mapped onto data cache depending on your cache management policies. So, what is really there for scratch pad memory and what is its distinction with cache? SPM data memory residing on chip, and it is mapped into an address space which is disjoint from off chip memory. As we have seen in the diagram, both cache and scratch pad memory allows fast access, whereas off-chip requires longer access time. But what is important to note is that Scratchpad guarantees single cycle access, whereas an access to cache is subject to cache miss. Because I have got a small cache memory and the complete DRAM area is mapped onto cache area. So, obviously, the entire DRAM is not stored in cache. So, there would be cache miss. When there is a cache miss, obviously, my CPU is not accessing data in one cycle. So, it is not guaranteed one cycle. But since SPM is occupying a part of the address space of the processor itself, so the access to SPM is guaranteed to be completed in one cycle. So, the basic advantage of using SPM, okay, on chip memory which is built with high speed RAM, okay, the basic advantage is that it is a guaranteed access. If a location is mapped to SPM, there will be always a guaranteed access. So, typically your critical routines or mostly access routines is expected to be stored there, as well as data which is to be used very frequently or to be used in a compute intensive fashion should be accommodated in SPM. So, cache, as I have already told you, is a small fast memory that holds copies of some of the contents of main memory and not definitely the entire content. And the whole logic of having cache, and today you will find cache in many of these embedded processors and particularly embedded microcontroller chips, there is on chip cache. They are being used to speed up the access, exploiting what we call temporal locality as well as spatial locality. The basic principle of temporal locality is that if we are accessing a data or an instruction now, it is very likely that I shall be accessing that instruction soon. Okay. So, once an instruction or a data element being loaded into the cache, what is likely that CPU next time will access that data or instruction from cache, and hence that access will be much faster. Associated with this is a principle of spatial locality. That means, when you are loading an data item or an instruction into the cache, you typically load not just a single instruction or a single data element, but a block of data element or a block of instructions which are located near to the current instruction in the memory address space, because it is very likely that these instructions would be currently needed for execution. So, typical example could be a loop. So, if you are executing a loop, it is very likely that a set of instructions will be executed which are in the neighborhood of the current instruction in the memory address spaces, and these instructions would be accessed frequently in recent times. Therefore, they also satisfy the property of temporal locality. In fact, a cache controller mediates between the CPU and main memory. So, pictorially it looks something like this. You have a CPU and you have a cache controller, you have these as cache, and this is your main memory. So, according to this model, so whatever address a CPU generates, that is processed by the cache controller to find out whether the data is typically in the cache or not, and if it is so, if the data is there in the cache, the data will be passed on to CPU, or there is a need to access main memory. So, data from the main memory is needed to be loaded onto the cache and at the same time may be passed on to the CPU. So, basic sequence of operations, if you see, this is CPU generates address, depending on where it is located, either on the cache or main memory. Cache controller figures that out, and when it gets a data in the cache, that is returned. If it is not so, what will happen is you have to get the data from the main memory, and at the same time that data gets loaded also into the cache. So when you get the data in the cache, what we say is cache hit. When you don't get data in the cache, what happens is cache miss. So when it's a cache miss, obviously processor is not accessing data or an instruction in a single clock cycle, and therefore what we say that when we use cache, the performance of processor is not completely predictable. So cache controller uses different portions of the address issued by the processor during a memory request to select parts of cache memory, and how it uses these addresses depends upon the organization of a cache that is being adopted. So let us look at some of these definitions. Working set. What is really working set? Is a set of memory locations that CPU refers to at any one time. This one time obviously has associated with it a concept of granularity, that is a sequence of instructions is what is being referred to as one time. Cache hit, as I have already explained, happens when an address requested by CPU is found in cache. The cache miss is when the location is not in cache. There are different types of cache miss. The first one is called compulsory miss or cold miss. It occurs the first time a location is used. So whenever a location is referred to in the memory, if it has not been used before, obviously that data is not expected to be in cache, because a cache management policy typically follows load on demand. So that is what we call compulsory miss or cold miss. Capacity miss occurs when you have a too large working set. That means you are accessing a set of instructions, okay, frequently, but this set of instructions is large enough such that it cannot be accommodated completely into the cache. This may happen with a data area as well. You may be processing a large enough data block which cannot be accommodated in the cache. That means that your working set is not small enough to be accommodated in the cache that you have implemented. That is what is known as capacity miss. Conflict miss is when two locations map to the same location in the cache. This would happen because you are mapping a DRAM area, the main memory area, which is pretty large, onto a small cache. Therefore, whatever be the caching policy you follow, a number of locations from the main memory would be mapped onto a single location in the cache. So, if you are accessing two such locations, there would be a conflict and cache miss. So, if we look at now cache operation, when a miss occurs, the miss can be any one of these types of miss. It would cause cache controller to copy the data from main memory to cache. Data is forwarded to the CPU at the same time, and this phenomena is known as data streaming. And if that block is already occupied, then that data has to be evicted out and replaced by the content of memory addresses currently requested by CPU. And when such a thing happens, you load just not a single location, content of a single location, but content of a block to exploit what we call spatial locality. So when you are evicting, what we have to take care of? We have to take care of the fact whether the data which was contained in the cache has been modified or not. If it has been modified, I need to figure out a mechanism to store back that data into the main memory or DRAM memory. So, for that purpose, typically you associate a bit which is called dirty bit. It is a status bit associated with the cache memory to indicate whether the cache content has been changed or not. So, obviously, if the dirty bit is set, that means that block has to be written back to the memory, otherwise you need not write back, and obviously write back would imply a performance overhead. So, let us see different caching mechanism. First, we shall look at simplest caching scheme, which is direct mapped cache. So, in direct mapped cache, each memory address is associated with one possible block within cache. Therefore, what happens? To look for a data or look for an instruction, the cache controller needs to look at a single location to find out whether that data or instruction exists in cache or not. And in fact, what we typically say that the whole transfer takes place in terms of block. So, you search for a block at a fixed location in the cache. So, this is a very straightforward, you map a set of memory locations to a single block in the cache. Okay? So, when a particular memory is accessed and that data is not there in the cache, you fetch that data from the memory and load it at that location. So, let us say this is my memory, this is just has got 16 locations and you have got your cache which has just got 4 locations. In a direct map cache, what will happen is there is a mapping which is already defined. So, in this case I have defined a mapping that 0 goes to 0, 4 goes to, that is 4th location goes to 0. Similarly, that the every multiple of 4, that 0 goes to 0th location, 1 goes to 1 location, 2 goes to the second, 3 goes to 3, and now 4th location goes to 0. Similarly, your 8th location goes to 0. So, you can see that multiple locations are getting mapped to a single cache block. Now, obviously what will happen is in this case when you are accessing a memory location say 0, if this block is empty, you will load this data onto this block and not to any other block. So, it is very easy for the cache controller to find out whether the data is there in the cache or not. So, here the assumption, if we work with simple assumption that block size is 1 byte, the cache location 0 can be occupied by the data from memory location 0, 4, 8 and so on, and in the general case a fixed mapping from memory locations to that of the cache. So, how is it really done or how is it really implemented by the cache controller? For that purpose, actually the address that is being generated by the processor is logically divided into these blocks. We call CAD the tag, index, offset block. So, this is the division of the memory address that is being generated by the processor. So, what you have, this is your cache block. In the cache block, what you store? You store data definitely, and there can be multiple bytes of data stored here in a block, but along with you stored the tag and stored another bit, a valid bit, which tells you whether the cache block contains really the data from the main memory or it is just a junk. Index, so I told you that address is divided into 3 portions. This is your index. Index is used to select which cache block to check. In fact, there may be multiple such cache blocks. The tag information, the tag part of the address is compared with the tag part of the cache memory which is already stored. So, if these 2 tags do match, that means there is a cache hit. If there is a cache hit, then you get the value. So, this is what happens in a direct map cache. So, you realize that 2 regularly used memory locations, if they map to the same location, then that would lead to what we call conflict misses. So, this direct mapped cache suffers from the problem of what we call conflict misses, because there are these locations, multiple locations map to a single location in cache. So, even if cache is other locations of cache is empty, if I access these locations regularly, then there will be a conflict miss and the worst case performance will be really bad. So, this is what we are trying to show here. So, you have a tag. So, this tag using the index I have got to a particular block, looking at the tag, I compare the tag, and then on the basis of that I shall say whether it is a hit or not. If this equals, then there is a hit, and then I shall get the data which is a byte. Now, this logic is what is implemented by the cache controller. This logic is what is implemented by the cache controller along with other things as well, the whole policy part as well. So, this is an example in with respect to ARM architecture. So, you have got an address. Okay. So, the address part, if you see that this is a tag part, the index part is directly being fed to the decoder to select the cache block. Okay. Then what you are doing? Yeah, there is a tag RAM apart from actually the data RAM, which contains multiple bytes, that is a block as a whole. So, you have got a tag RAM. So, this tag RAM is used to get the tag, and this part is compared with this part of the address. So, this tells you a hit, and accordingly the data would be provided. So, this hit will be used for enabling the appropriate input line for the multiplexer. Next, we get what we call set associative cache. So, the basic issue of the set associative cache is to remove the problem of conflict misses that you frequently encounter in your direct mapped cache. A set associative cache is characterized by a number of sets. Okay, there is not a single set or a single block, there are a number of sets. And each set is actually mapped or implemented by direct mapped cache mechanism that we have so far discussed. So, memory locations map onto blocks as in direct mapped cache, and there are n separate blocks for each memory location. So, since there are multiple cache blocks or cache sets, therefore, a memory location now gets mapped onto n different blocks, because you have used n different cache sets or cache blocks. Okay. And each request for an address, it is broadcasted to all sets simultaneously. Okay. And if any of the sets has a location, the cache reports a hit. So, I hope you have understood why this arrangement minimizes conflict misses, because multiple locations now gets mapped onto not a single location, but onto different cache blocks. So, even if we are accessing this kind of locations which are having identical mapping on a regular basis, it is very likely that I shall find them in different cache blocks and I shall not generate cache miss faults. So, let us see its actual implementation. So, I have got a set of direct mapped cache, these are different sets. Okay. So, my hit can come from any of these sets, because a given memory block gets mapped onto a block in this cache, and since there are n such sets, so it can get mapped onto any one of these blocks in any one of these sets. So, the hit logic will come from any one of these blocks. Okay. So, it has got less miss rate compared to that of your direct mapped cache, but obviously it will be slower than direct mapped cache, because you have to now take into account so many comparisons. In a typical ARM implementation, if we have two-way set associative cache, you see that this organization is very similar, just like that of your direct map cache. Instead of one block, now we have got two blocks. Okay, this is a two-way, that is why we are calling it two-way set associative cache. So, the decoder, that same index part is used to find out the block, okay, and this tag is now compared with the address part. So, it can be either here or it can be in this block. So, I do the comparison. So, there are two comparator blocks. Okay. Depending on the output of the comparison, I enable the corresponding output of the multiplexer. Okay. So, one of them will have the data. So, I enable, and the control signal for this multiplexer effectively comes from the result of this comparison. So, this is how a two-way set associative cache is implemented. Obviously, your miss error in this case is expected to be much less. The other way of really looking into the cache is, or increase its efficiency, is to use what we call CAM, or content addressable cache memory. Now, in a way, CAM implements a fully associative cache. That means, without really mapping each location of the memory to one location in the cache, instead of doing that, in an intelligent way, CAM implements almost a fully associative cache. The basic idea is that it uses, now we can think in these terms, that we have got a set of comparators, and that comparator compares the input tag address with a cache tag stored in each valid cache block. So, I am doing many such comparisons in parallel. Okay. Now, effectively what does that mean? That if I can do that comparison, and if that comparison is successful, I would like to have, on the basis of the comparison, the actual address. Okay. So, the organization now is slightly different. Okay. So, in principle, if you just consider that I have got two-way associative cache, and if I increase the number, that number of sets that we are using, we increase that number, effectively what are we getting? A location can be mapped to any of these sets. So, the miss rate would be much less, but we cannot really have that much hardware on chip, because having that hardware would essentially imply area as well as energy overhead. So, you use what is called a CAM. So, CAM works effectively like that of your RAM, but slightly in a different way. Okay. CAM produces an address if a given data value exists in memory. Okay. So, that is the basic reason why we call CAM a content addressable memory. Okay. So, the basic idea is that I take the tag, just consider in this way. So, the moment I take the tag, if I can use the tag to get the address, okay, which is really stored in the cache, okay, and I use the tag to generate that address in the cache, I have effectively done almost a fully associative memory. So, let us see how it gets implemented. So, you have got the address. Okay. Now, this address is fed to what is called a tag CAM. Fine. So, once it feds to tag CAM, so this is something like your memory itself, but it takes in this as input, okay, and produces address. Address of what? Address of the location in the cache which contains the data of this location. So, now it becomes fully associative. Okay. We can see what was the reason of going into n way set associative. We are trying to approximate the requirement that I would like to map any memory location to any free location in the cache. That is my target. Now, if I have to do that using simple comparators, I have to do what? Compare tag of each and every location of the cache. So, it becomes a sequential comparison, and that will not really help me in fast access. So, to overcome that problem, we had suggested n way set associative cache. That means I map to n such sets and find out which set has got the data from my target location. In case of CAM, what we are doing, you are just reorganizing the whole RAM, that is your tag RAM as well as your cache. So, you are using this address part, what we are showing here is a combination of both of your tag as well as the index together. You are using that, you can consider this is an address which is going into this tag CAM, which is a content addressable memory. So, depending on this address, what the tag CAM is generating address of the location in the cache. So, effectively we are doing many such comparisons in parallel, but instead of using many such comparators, we have intelligently used the address of this memory to generate address of the corresponding location in the cache. Okay. So, CAM in that way is an efficient organization, and CAM is used in architectures, ARM architectures like 920T and ARM 940T. These are for cache implementations, they use this kind of CAM based approach. So, if you look at now cache in a microcontroller. So, actually in a microcontroller core, how does the cache is really used? If I am having a von Neumann architecture, obviously I shall be having an unified cache, a single cache for instruction as well as data. For Harvard architecture, we shall have two caches. So, this we call split cache organization. I have instruction cache and data cache separately. A small fast FIFO that temporarily holds data that processor would write to main memory is used in many a times along with cache. Now, why this buffer is used? The basic idea of using this buffer is, if you remember, I talked about the basic problem of writing. Okay. So, when I am writing it back, so write back may require a kind of an overhead. So, in order to take care of that overhead, many a times these processors including ARM have got on chip write buffer, which is a fast memory, but it is not same as that of cache. Okay. So, buffer is emptied to slower main memory, and it reduces time for processor to write small blocks of sequential data to main memory. So, instead of writing the data directly onto the main memory, what processor does is that it writes data onto the write buffer, and from the write buffer the data is stored back onto the memory of the processor. Obviously, write buffers improve cache performance, because cache controller during block eviction writes dirty block, that is a block for which the dirty bit is set, to the write buffer instead of writing it back to the main memory. So, processor is not suffering, because see, you should understand that while this write back is taking place from a dirty block of cache to the main memory, the processor has to wait when there is a miss, and the miss requires a block eviction. So, if I can use a write buffer which is a fast memory, so that eviction will take place fast. So, processor now needs to wait only for the time required to load the data from main memory to the cache, and at the same time data is being streamed in. If I would not have got a write buffer, the time taken would have been double when there is a block eviction, because if I consider that access time for read and write is similar, so you have to first write back a block, and then you have to read the block, and after that only the processor can really start execution. So, that time can be reduced by using this write buffer. So, pictorially you have got a write buffer at this path. I have not shown the other path from CPU. CPU can also have one path directly onto the write buffer if it is required, and you have got this cache. So, cache transfers. So, this is a typical scenario which would take place. Okay, this would take place when there is a transfer of the data from cache to the main memory. These write buffers in many cases are implemented as FIFO memory. Okay, you have seen hardware stack memory, where in PEEK, where you can push the PC in case of a subroutine call or an interrupt. This is an example where in many cases you have hardware FIFO memory. So, effectively a queue. Why it is a queue? Simply because I am storing the data sequentially. In many architectures, these write buffers are not also implemented as a queue, but in a different way. So, say for example, ARM10 family supports what is called coalescing. That means you can write the data and they are grouped together, and then the group or a block is transferred from the write buffer to the main memory. Now, obviously, the issue that comes up in this context is that the data in the main memory and the data in the write buffer are obviously not consistent. Why? The data might have changed, okay, and that data is written into the write buffer, and the data in the main memory is not yet updated. So, that is an important concern when you are programming the system. So, now obviously all these issues takes us to different kinds of cache policies which are to be adopted. So, write policy, I can have a write through or write back. Okay. So, if you really do not want to have inconsistency as a problem, I would like to implement what we call a write through policy. Okay. So, in a write through policy, cache controller writes to both cache and memory at the same time. A variant of this policy would be writing to cache as well as to the write buffer, so that that can be emptied later on, but it will not wait. That means cache controller is not waiting for the write process to be initiated till a block eviction takes place. Obviously, this write through policy would have overhead when you are writing onto the main memory, and if you are frequently writing, that can really slow down your execution. Now, you should keep in mind also the other fact that of energy consumption, because accessing of main memory, okay, that is your DRAM, will consume more energy in many cases, okay, because cache, that although they are static RAM, they are also in many cases optimized in terms of energy requirement for access. In case of write back, the policy that we were talking about, and write back policy really requires this dirty bit, okay, and in the write back you actually wait till the block eviction takes place. When the block eviction takes place, then only you will write back the data either to the memory or to the write buffer, as the case may be. Obviously, this has a problem, as I was discussing earlier, that of inconsistency of the data for a longer period. Next thing is block replacement policy. If we are talking about a block eviction, which block is to be evicted? That is, which block is to be replaced? Because you may find that if we are talking about n-way set associative cache, so there can be n such locations where a set of memory locations can be accommodated. Now, block eviction would take place when n such blocks are filled up. So, for eviction, the cache controller has to decide which block is to be evicted, okay, has to decide which block has to be evicted. The simple policy is round robin or cyclic replacement. Now, that means the block, okay, which is loaded currently will obviously not be replaced. So, you go through a round robin procedure and you start from the current block and you go back and find out the next block which is in line to be replaced and you replace it. Now, obviously, this round robin or cyclic replacement gives you a predictable performance because you exactly know the sequence in which the blocks are to be replaced. But it can also have very bad worst case performance. Why? Because if you have say n blocks and these n blocks are being accessed, okay, and it is arranged in such a way that the next block that you will access becomes the next block according to the round robin policy to be replaced, then you will be actually doing thrashing. That is, you are loading a block onto the cache, again evicting a block from the cache. So, in fact, round robin policy can give rise to a very bad worst case performance for the cache. So, that is why in many cases this random selection is another policy which is implemented. Okay. Now, you can realize that when we are talking about these block replacement policies, these policies have to be implemented in hardware in the cache controller. So, really I do not have an option of going into very sophisticated policies. So, a block replacement using round robin is simply a ring of counter, that is I start with a value and a modulus counter. Simply a modulus counter will give me an implementation of a round robin, and a random selection is a random number generator effectively within a block, and that can also be very easily implemented in hardware. The next thing is allocation policy. When is really a cache block allocated? That means when is that block from the main memory is loaded onto the cache. So, this is what is known as your allocation policy. So, you have typically a read allocate and read write allocate. A read allocate policy means that allocation of the cache takes place only on read. Okay. When it is a write access may not really mean that that location would be accessed again, and typically it is true when you are looking at an unified cache. Okay. So, you are executing a sequence of instructions. You might be writing the result onto a location in the memory. So, that may be written only once. It may not be true that the locations around that write memory area would be accessed very frequently in near future. So, read write allocation policy only tries to take care of the fact that if you are really writing onto that location, that means that data area you are likely to access. So, a very simple example could be an array access. So, if you are likely to modify one element in that array, you are very likely to modify other elements of the array. So, in that case, even when there is a write operation, you would like to allocate that block in cache. Otherwise, a typical instruction execution would necessitate a read allocate policy. Now, these policies are always a part of what I call hardware policies implemented in the hardware. So, if we look at now ARM, this is a typical example of a microcontroller where these policies, availability of the policies are there. So, these are cached core. So, ARM 7 and ARM 9, I have picked up some examples of ARM 7 and ARM 9, that is what we had discussed. So, they implement write through policy, write through, the replacement is random, okay, and your allocation policy is read miss, okay. And in case of this is same true is for ARM 740T. If you look at ARM 920T, you have an option of write through as well as write back, random and round robin. Similar thing is true for ARM 946E, some of the ARM, advanced ARM, ARM 10 and 11, they have also read-write means options. Now, these are actually options which are to be selected for the purpose of cache implementation, and these are available as part of the core policy. Okay. Now, how are these things really implemented in case of a microcontroller? Because these are policy are available, but how they are made available and how they are to be really used. So, that leads us to the issue of cache control in ARM. So, if you are looking at the cache management in an embedded system, you have to have these mechanisms available on the embedded controller itself to manage the cache. In fact, typically today you have got what we call on-chip cache. So, an SoC designer who picks up that ARM core as an IP will make use of this option and configure the cache, because he is putting the cache along with the core, and you as an external programmer will not really have option to play with them in many cases. Okay. So, these options are actually options which should be available to an SoC designer. So, all standards for this purpose, ARM core has got some facilities. In fact, we had discussed coprocessor instructions and use of coprocessor in ARM. So, the most important coprocessor that ARM uses is coprocessor 15, and this coprocessor is called system control coprocessor, and whose job is to manage its standard memory facilities including cache. CP15 has registers. So, you program this coprocessor by writing onto the registers by using appropriate instructions, the coprocessor instructions I had discussed earlier. So, CP15 has registers using which different features and control functions of cache can be specified. You can specify size of cache and degree of associativity. This would depend on how the cache is actually getting implemented. You can enable or disable cache operations. You can also execute policy choices like write, replacement and allocation. There are also other kind of control functions like flushing of cache, which can be initiated by an instructions onto the cache coprocessor. Okay. That is your system control coprocessor. Some aspects of it is predetermined, because if since they are determined by the additional hardware which are being put in place, some aspects of it are available to the external programmer, so that he can exercise the control on the cache management through this coprocessor. In fact, this coprocessor is actually what is the block that we have seen, the cache controller. So, this cache controller manages the complete cache access for the case of ARM. In fact, ARM cache controller provides another interesting feature. In fact, what we talked about in case of SPM, scratchpad memory, that occupies a part of the address space of the processor itself. Since it occupies a part of the address space, what is the advantage? You get a guaranteed access. Okay. And there is no question of cache hit or miss, because you are not doing any kind of a mapping. Now, ARM provides for a kind of idea which is called lockable cache. Okay. So, a part of the code can be locked into the cache. The other important issue related to the cache in ARM is that of memory areas being indicated cacheable or not. Okay. Because in my original diagram, the first diagram I had shown that my entire memory space which is occupied by the DRAM is getting mapped onto the cache. But if you remember the IO management of ARM, in ARM what do we use? We use memory mapped IO. So, IO ports are located in the memory. Now, data in a memory port if it is an input port, can change asynchronously, can be changed because of the external source. So, if I now make those memory locations cacheable, actually I am getting an inconsistent data. In the cache I am having a data which is not the true data. So, those locations typically will not be cacheable. In fact, the locations which are mapped onto the peripheral processors, that is IO devices, they would be typically not cacheable. And in many cases, they will not be also bufferable when you are using a write buffer. Say for example, when you have got an interrupt from a processor, you have got an interrupt and you would like to write back to the processor acknowledging that you are servicing that interrupt, okay, from that IO device. Now, if that write is written onto the buffer, then what will happen? There will be a time expiry before that is written onto the device. So, in between device can again raise an interrupt which is not equally called for. So, such locations may not be also bufferable. So, for memory mapped IO processes and memory mapped IO processors in particularly, this cacheable memory area or bufferable memory area is an important considerations, and these cache controllers typically has got the provision for indicating whether some area can be cached or not. This cache lockdown is other point that I was discussing already, that I would like to have some critical code and data to be loaded into cache in such a way that corresponding cache blocks are not reallocated. Okay? So, because these will be repeatedly used. In fact, the whole purpose of using SPM also is something similar. In the SPM also we can have the critical code which will never be replaced because it is part of your memory itself, memory map itself. Now, in case of ARM, they provide this similar facility for cache, because if I can do it in the cache, then some critical part can already be loaded onto the cache which would be repeatedly used. Okay. And for lockdown purpose, cache in ARM is divided into what we call lockdown blocks. So, one block from each cache set can be marked as locked block. Okay. So, your data from main memory can be loaded onto these blocks. So, that will not be really replaced. Now, you will find, if you remember, we had talked about even in the DSP processors, we had talked about loop cache. That means frequently accessed loops being loaded onto the cache, so that there is a minimum overhead for loop execution. That also has got a similar idea, that there is a dedicated memory where you store a particular loop which is very frequently used, and you may force it not to be replaced at all. Okay. So, there are various combinations of these. These may be locked for a long time, may be locked for a local time period, depending on the nature of the code or the application. Next question is that of multi-level caching. Although today most of the embedded systems come with level 1 cache, but advanced embedded processor architectures are supporting multiple levels of cache. So, obviously, this is to minimize what we call capacity miss, to minimize cache miss rate due to limitations in capacity. System designers may add what is called level 2 or L2 cache. L1 cache will have normally single cycle access, and L2 cache will have latency of more than one CPU cycle, but less than that of main system memory. So, that would speed up the operations. In fact, interestingly, look at this kind of a hierarchical memory architecture which are being propounded and proposed and actually being implemented in various SOCs. So, here we have shown 3 levels of cache: L0, L1. So, we are not talking just L1, we are talking about L0, L1, L2. These are on processor cache, and then you have got DRAM banks. So, these are all separated into banks. And why this architecture is being proposed? Obviously, it would optimize data transfer rate. Optimizing data transfer rate would imply that the capacity miss which would be there, if I just use 1 to 16K and it is the first is memory and costliest memory, this other optimization happens in terms of cost, then that would be taken care by L1 as well as by L2. Okay. And even when it is not really in L2, you will be really accessing the DRAM banks. And energy requirement for DRAM access is more than that 10 times of that of L2 access. So, in effect what we are talking about is that we are optimizing energy utilization as well. In fact, this concept of energy leads us to what we call energy aware memory organization. And typical, the memory is partitioned into blocks. Okay. Blocks are enabled or disabled independently, and energy for memory access is less when memory banks are small, but large number of small banks is area inefficient and can impose wearing overhead. So, energy is an important consideration for all embedded systems and particularly battery powered embedded systems. So far we have looked at use of cache, okay, to speed up, and we said that cache, using multi-level cache, you can also have energy optimization. But what about actually memory organization, okay, in terms of blocks? Because I told you that you are driving, if you are driving a long bit line, that would actually lead to more energy because you need more current to drive a longish bit line. So, if you divide your memory into blocks, what happens? Just look at this example, that this is a memory area which are using 0 to 7 address bits, that is you are having a 8-bit address bus, and this memory is divided into 2 blocks. So, the number of locations that are to be driven at a given point in time is 128, it is half of that of the complete block, and this block would be deactivated because you are using a 2 by 1 decoder depending on the address bit 7, that is the most significant address bit. So, effectively your energy consumption would be less. So, this is a suggestion for using smaller memory blocks. So, your energy consumption for accessing one of these banks at a given point of time would be less, because energy is a very important consideration for memory organization in embedded system as well. So, what we have studied today is organization of memory in embedded systems. We have looked at the use of cache and different policies being used for management of cache. In the next class, we shall discuss memory management, in particular virtual memory and protection issues.